turned to two radio astronomers named Masaki Morimoto and Hisashi Hirabayashi. They eventually chose the star Altair because it's very bright and relatively close. It was also selected because the message was planned to be transmitted during an annual Japanese festival known as Tanabata, which celebrates the meeting of two celestial deities represented by the stars Vega and Altair. Furthermore, Morimoto and Hirabayashi were asked to create their own message, and after 3 days of work, they came up with this: a sequence of 13 bitmaps measuring 71 by 71 pixels that were clearly inspired by the Arecibo message. The first 4 images depict things like natural numbers, prime numbers, basic math, common elements, the solar system, and essential building blocks of DNA. The next 8 illustrate the evolution of life from simple organisms to jellyfish, fish, amphibians, dinosaurs, apparently not Bigfoot, a family of humans, and a close-up of a woman's face. The final bitmap depicts a crude illustration of the Stanford radio telescope alongside information like its radius, wavelength of the transmission, and total number of bits in the message. We also find the word toast written in plain English. According to Hirabayashi, during the 3-day stint when he and Morimoto conceived of these images, they weren't necessarily sober the whole way through. This may or may not have influenced their decision to include the Japanese and English word for toast, equated to the chemical formula for ethanol. Because Weekly Shonen Jump targets a very young demographic, the magazine tried to clean this up a bit by reframing what was clearly an afterthought by two half-drunk astronomers as
a toast between Japan and the United States.
Nevertheless, for about an hour on August 15, 1983, the 13-bitmap maps and an audio recording of the abridged fan-submitted greetings were beamed towards Altair.
こんにちは、こんにちは、こんにちは。こちらは太陽系第3番目の惑星、地球です。この電波は青い宇宙船地球号からまだ会ったことのない友達、ET のあなたたちへ平和と友好の願いを込めて送信されました。この計画をして、日本という国の多くの子供たちからメッセージが寄せられました。私たちの地球はもうすぐ新しい世紀を迎えます。その21世紀にはあなたたちと会えるかもしれません。だからさようならは言いません。もう一度友情の挨拶を送ります。こんにちは、こんにちは、こんにちは。
Altair is among the brightest stars in the night sky, and at a distance of less than 17 light years, it's only, a few quadrillion stone throws away? In fact, Altair is so cosmically close that enough time has now passed for the transmission to have made a full round trip. That is to say, the message reached Altair back around the millennium shift, and we could have received the reply as early as 2017. Now, the fact that we never did does not necessarily mean there's nobody home. Perhaps they missed the brief 60-minute window when the message swept across their system. Perhaps they did pick it up, but they're still drafting a response. Perhaps they took one quick look at Earth and humanity and were like, nah, we good. While all of these scenarios are of course equally probable, the most equal is unfortunately the first one. Not only have astronomers failed to detect a planet around Altair, but even if one does exist, the star's only been around for about 100 million years. Compare that to a 4.6 billion year veteran like the Sun, and things start to look a bit bleak. Sure, there's always the possibility that intelligent life typically evolves much faster than it did here on Earth, but we currently have no good reason to think that's the case. But it gets worse because even if the Altairians did respond, the odds of us even noticing are extremely remote, because telescopes are expensive, in low supply, and high demand. Sacrificing years, months, or even just days worth of observation time to screen a single planetless star for alien signals ain't exactly top priority. It wasn't until the summer of 2023 that a team led by astronomer Shinya Narusawa secured a brief time slot at the Yasuda Deep Space Center in Japan to search for a belated response to the Altair message. Scheduled once again to coincide with the annual Tanabata Festival, The search began late in the evening on August the 22nd and lasted for a grand total of 60 minutes. Remaining optimistic, Narasawa told reporters the following morning that they wouldn't immediately know if an alien signal had been detected because it would take a long time to analyze the terabytes of collected data. But given the lack of updates since then, I wouldn't keep my hopes up on this one. If nothing else, the message to Altair was received loud and clear by thousands of children across Japan. In fact, Call to the Cosmos seems to have had a bit of a rippling effect because a whole series of messages designed by Japanese children would later be transmitted for several years in a row. But before we get to all of that, we're going to take a brief detour into the dazzling world of censorship. As mentioned before, when the public became aware that NASA had bolted a plaque to the side of Pioneer 10, not everyone approved. But it wasn't just about the risk of attracting dangerous aliens, it was also about modesty. You see, some people were absolutely mortified to learn that the plaques featured line drawings of two naked humans engaged in the scandalous act of standing there.
I must say, I was shocked by the blatant display of both male and female sex organs on the front page of the Los Angeles Times. Surely, this type of sexual exploitation is below the standards our community has come to expect from the Times. Isn't it bad enough that we must tolerate the bombardment of pornography through the media of film and smut magazines? Isn't it bad enough that our own space agency officials have found it necessary to spread this filth even beyond our own solar system?
As amusing as that is, the controversy surrounding the plaque's nudity has been somewhat exaggerated over the years. These puritanical takes were muted and few, to quote Carl Sagan, and it's genuinely difficult to find examples like the one you just heard. There were a handful of reductive headlines, and some newspapers opted for the Barbie and Ken doll treatment, but the vast majority published the full, uncensored image and barely even mentioned the couple. In fact, some criticized the plaques not for showing the human form, but for not showing enough. More specifically, people took issue with the complete absence of visible female genitalia, considering that no such neutering had been applied to the man. It's unclear if the lack of anatomical detail on the lower half of the woman was demanded by prudish NASA officials or a decision made by the Sagans themselves. Conflicting accounts makes it difficult to know exactly who's to blame. Nevertheless, when it came time to select material for the Golden Records a few years later, these concerns flared up again. Fearing a repeat of the previous debacle, NASA religiously vetted every song, soundbite and image that Sagan and co sought to include. They ultimately rejected a nude photograph of a young man and pregnant woman intended to show both human anatomy and procreation. The reason I'm bringing this up is because in 1986, an American artist by the name of Joe Davis decided to fight back against all this pearl-clutching with a project known as Poetica Vaginal. With the help of a few ballerinas and other volunteers, Davis used a custom-made device to record, how do I put this? Contractions from within the female reproductive system. Those pressure oscillations were then artistically manipulated to create something that's meant to resemble human speech. After obtaining access to a radio telescope near the Massachusetts Institute of Technology, Davis and his team began transmitting the sounds into space. However, the broadcast only lasted for about 15 to 20 minutes before the project was prematurely terminated by an Air Force colonel who was apparently overseeing the facility. Nevertheless, according to Davis, those few minutes were enough to transmit brief snippets of audio to each of the 4 selected targets. 2 of them were never publicly identified as far as I can tell, while the other 2 are known as Epsilon Eridani and Tau Ceti. Epsilon Eridani is home to one confirmed planet with a mass nearly identical to that of Jupiter. While additional planets could exist, including ones that resemble Earth, Eridani is a relative newcomer to the Milky Way family at approximately 500 million years young. On the other hand, Tau Ceti is certifiably ancient. Its precise age remains unclear, but it's definitely older than the Sun and home to not just 1 but 4 confirmed planets. On top of that, there's a slim chance that 2 of them are grazing the inner and outer bounds of the habitable zone, that being the distance from the star at which water could remain liquid on the surface of an Earth-like planet. Unfortunately, both of these stars are surrounded by immense belts of debris, not unlike the asteroid and Kuiper belts in the solar system. The difference is that Epsilon Eridani and Tau Ceti retain asteroidal and cometary populations many times greater than what currently orbits the Sun. While this makes perfect sense for a youngster like Eridani, it's a lot more concerning for a galactic grandparent like Tau Ceti. It implies that something is either preventing that material from coalescing into planets across billions of years, or that the system has suffered a recent cascade of instability. In either case, more stuff almost certainly means more impact events, like the one that nearly wiped out the dinosaurs. But even if we optimistically assume that none of that's a problem, the mass and size of the planets orbiting Tau Ceti are highly uncertain. There's a good chance they have less in common with Earth, and more so with Uranus and Neptune. But even if that isn't the case, the chemical makeup of Tau Ceti appears to be quite different from the Sun, suggesting its planets are composed of materials quite different from those that spawned life in the solar system. In summary, it's not looking great. Now, it may seem pointless to consider the habitability of these distant worlds when the message we send towards them is completely indecipherable. I mean, if you thought the aliens were going to struggle with the golden records, good luck to them figuring this out. But just like the Arecibo message, the artificial nature of the signal is a message in and of itself. If you want to believe there's a naturally occurring phenomenon capable of producing the exact same radio waves as those emitted by Joe Davis and his team back in 1986, you go right ahead. But somehow I have my doubts about that. Presuming the message was received and correctly identified as a technosignature, we could have received a reply from the Eridanians as early as 2007, or the Cetinites as early as 2010. I did some checking and regretfully have to inform you that humanity's been ghosted once again. About a decade after the message to Altair, the National Space Development Agency of Japan began hosting an annual space camp event for young children known as the Cosmic College. Students could choose from a bunch of different activities over the course of multiple days, including a class on how to write and send interstellar messages. In fact, one of the astronomers invited to lecture at these events was none other than Hisashi Hirabayashi, one of the creators of the Altair message. But it wasn't just a theoretical exercise. NASA actually arranged for some of those messages to be transmitted into space. Once a year, between at least 1995 and 1998, simple bitmap images measuring 11 by 11 pixels were sent from the Yasuda Deep Space Center to various locations across the galaxy. These transmissions received next to no publicity at the time and are virtually unknown to this day. This makes it difficult to know exactly what was sent where and when. Here's what we do know. The first Cosmic College was held in August 1995, during which this image of two parents and a child was beamed towards some unknown destination within the constellation Libra. Even less is known about this image of an alien holding hands with a human, transmitted sometime in August 1996. This time we don't even know the general region of the sky to which it might have been sent. In August 1997, two bitmaps were beamed towards a binary star system known as Spica. The first image depicts a smiley face, while the other shows a Japanese dumpling known as a dango next to a steaming cup of tea. Unfortunately, Spica is a ticking time bomb because the two stars are expected to slowly encroach upon one another, which could trigger a supernova at some point in the future. Even if that wasn't the case, they're far too young to host an Earth-like planet, and even if that wasn't the case, it would take another 5 centuries for any replies to reach us. Finally, this image that simply says 1 + 1 = 2 was transmitted to some unknown location in August 1998. Now, there could be more of these transmissions that have been lost to time. For instance, an image of a leaf to symbolize the nature of Earth appears to have been designed during the Cosmic College of 1999, but I couldn't find any information on whether it was actually beamed into space. While competitions, art projects, and recreational programs certainly could generate an alien response, their primary function is to elicit a response from us down here on Earth. They're inspiring, provocative, and generally attract a lot of attention. So it was only a matter of time before someone came along and began charging a fee. In early 1998, American entrepreneur Charles Schaefer announced a commercial venture known as Encounter 2001. The project sought to crowdfund the launch of a tiny, light-sailing spacecraft that would carry samples of human DNA beyond the solar system. For only $50, anyone could submit a few strands of hair along with a brief message and their portrait and join the so-called Millennial Voyage. Market analysis by Schaefer and his team projected sales of anywhere between 1.5 and 4.5 million tickets before the launch date. If those figures seem a bit optimistic, they were nothing compared to the expectations of their customers.
Me and my girlfriend can't have children, and in a deep philosophical way, this may be one way for my genetic makeup to live on, with a minute chance that it might be recovered by another species and we might be recreated, and I could fall in love with my girlfriend all over again on another planet.
This idea that aliens might one day use your DNA to clone your body was surprisingly prevalent. For instance, the greeting submitted by renowned science fiction author Sir Arthur C. Clarke simply read, "Farewell, my clone." While the Millennial Voyage was the project's main objective, they also promised to beam participants' greetings into space ahead of the launch using a radio telescope, a side project that would come to be known as the Cosmic Calls. By spring of 1999, some 43,000 people had signed up for Encounter 2001, including two Canadian astrophysicists named Ivan de Til and Stéphane de Ma. De Til and de Ma had been given the task of creating what's known as a primer. A primer attempts to gradually introduce the recipients to more complex ideas using some sort of step-by-step process. For instance, the primer to the message to Altair were the 13 bitmaps sent alongside the far more complicated greeting in Japanese. De Til and de Ma did something similar for the Cosmic Calls. They created a primer composed of 23 bitmaps, and this first one starts off by listing the 10 digits of our decimal system using 3 different notations: unary, binary, and decimal. An idea they appear to have lifted from this image on the Golden Records, which did almost the exact same thing. But there is of course one very noticeable difference. The one from the Golden Records uses the familiar glyphs of Arabic numerals, whereas the primer to the Cosmic Calls uses these alien-looking symbols. That's because de Til and de Ma decided to create their own rudimentary language of sorts. Now, this might seem like an odd choice because whether, say, a 2 looks like this or like this, it's not going to make any difference to the recipients. But it's not about readability, it's about redundancy. You see, there's a lot of naturally occurring radiation that could interfere with the radio transmission between the source and destination. Imagine, for instance, that we transmitted 15 bits arranged like this to represent the number 8. If this one bit in the middle was flipped along the way, the recipients would pick up a 0 instead of an 8. Flip this bit and the 8 becomes a 6. Flip these two and it becomes a 5. In other words, this transmission has no redundancy whatsoever. Lose one bit and the entire message could become corrupted. The glyphs created by de Til and de Ma were designed to be as fault-tolerant and noise-resistant as possible. There are several bits of difference between all the symbols, and that still holds true even if they were to be mirrored or rotated. But apart from the symbolic difference, the Cosmic Call Primer follows a structure that should be very familiar at this point. The first 5 pages cover various mathematical concepts that gradually increase in complexity. The next 6 delve into chemistry and physics, including a schematic of the solar system. The next 8 are all about Earth, humanity, and biology, including a rendition of the Pioneer Couple and a 2-page map of the continents. Page 21 contains information about the transmission and telescope, while page 22 brags about our cosmological knowledge like the age of the universe. The 23rd and final page invites the aliens to respond by asking them a series of questions using this flower-looking glyph as a stand-in for a question mark. For instance, this means velocity, while this means photon, so this question could be read as, what is the speed of light? But how could the aliens possibly know that these symbols mean question, velocity, and photon? Well, it all comes down to that first page of numbers to which everything else is anchored. The aliens would start by hypothesizing that these 10 symbols represent 10 digits in a base 10 numeral system. With that assumption locked in place, they'd move on to the next page and find 1 something 1 equals 2. Okay, so they now suspect that this symbol represents addition and make similar assumptions regarding subtraction, multiplication, and division. Once they get to page 4, they'd know that this reads something plus 2 equals 3, while this reads something plus 4 equals 10. Given that the same symbol is used to represent what is clearly not the same value, they might suspect that this is a placeholder for a variable quantity. In other words, this variable represents something unknown, a bit like a question mark, emphasized by this symbol off to the left. By gradually introducing new symbols alongside familiar ones in such a way that logic and process of elimination can be used to fill in the blanks, it creates a lot of mutual corroboration between the pages. By page 8, they'd be introduced to the concepts of time and length via hydrogen, followed by velocity and photons via the speed of light. To be clear, there's still plenty of room for confusion and misinterpretation, not least of all because a few typos did actually slip through the cracks. For instance, according to this line on the 7th page, uranium is said to have 116 neutrons, but there is no such element. The lightest known isotope of uranium has 122 neutrons, and the most abundant here on Earth has 146, which is probably what they meant. But even if the primer had been flawless, there's only so much hand-holding one can do when you don't even know if the recipients have hands. In addition to the primer, the language created by the Tillandema was used to write the message about the Millennial Voyage. This was followed by a copy of the Arecibo message, greetings by the staff at Encounter 2001, as well as the 43,000 names and greetings from people around the world. With assistance from prominent Russian astronomer Alexander Zaitsev, Schaefer and his team then obtained access to the Eupatoria Deep Space Center in southern Ukraine, and the first cosmic call began broadcasting on May the 24th, 1999.
Greetings from Terra, or Earth, the third planet in the Sol system. As a member of the human race, I would like to extend goodwill to you and your race.
Give us a couple 100,000 years before you plan to visit us, please. Right now, we would have to run around saying, excuse the mess.
I hope the International Space Station program will succeed. I hope peaceful universe, and I hope we can find friends in the universe.
This message comes from 5th grade students of Earth, the third planet from the Sun and part of the Milky Way galaxy. We are peaceful humans. Please answer.
There is life and diversity everywhere you look on our world. I hope the same is true on your world. Life should be common and treasured.
Caution. We humans are a confusing and confused group of bipeds. We need guidance and desperately seek help for our very survival. We offer versatility, curiosity, humor, fear, and love.
Unlike many previous initiatives, which received very little attention from the press and public, the cosmic calls were a global phenomenon. In fact, the project received so much attention that officials at the National Space Agency of Ukraine got a bit spooked. The plan was to beam the message to 4 nearby star systems, but after the first transmission on May the 24th, Ukrainian officials suddenly shut the whole thing down. According to Zaitsev, rumors had begun circulating that the reason Encounter 2001 were using the Eupatoria Deep Space Center was because they'd been denied access to American facilities out of concern it might be dangerous to transmit messages into space. In reality, other radio observatories like Arecibo were simply not available on the dates requested. It had nothing to do with malevolent aliens. Zaitsev spent over a month explaining this to the agency before Schaefer and his team were allowed to resume broadcasting on the last day of June. The first target was 16 Cygni A sun-like star that's part of a ternary system. In other words, it's a system of 3 stars, with Cygni A being encircled by a small red dwarf labeled C, and together they orbit another sun-like star labeled B that's nearly 6 times further away than Voyager 1 is from the Sun. While Cygni B does have one confirmed planet, it's an enormous gas giant that patrols the entire habitable zone, making it impossible for an Earth-like planet within that region to maintain a stable orbit. While the transmission was specifically directed at Cygni A, The situation doesn't improve much because, as far as we know, it doesn't have any planets. Instead, it's orbited by Cygnus C at about twice the distance between the Sun and Pluto. It's definitely possible for an Earth-like planet to be sandwiched between them, but it all comes down to the precise orbit of Cygnus C, which is currently unknown. The second target was Gliese 746, a binary system composed of a Sun-like primary and a smaller companion of which very little is known. The distance between them is less than that between the Sun and Mercury, so there's no chance of finding an Earth-like planet in a stable orbit around either one. However, there is such a thing as circumbinary planets that orbit two stars at once. With a system as tightly bound as Gliese 746, there's plenty of space for such a planet to exist, but so far, nothing. The third target was 15 Sagittae. It could be described as a binary system because Sagittae A is orbited by this tiny companion labeled B, but Sagittae B is what's known as a brown dwarf that falls somewhere between a planet and a star. It's dozens of times more massive than all the planets in the solar system combined, but still not quite massive enough to shine like a star. Apart from Sagittae B, no other bodies have been detected, and the system is a bit on the younger side at approximately 2.5 billion years old. Finally, the fourth target was Gliese 777a, a Sun-like star that is once again encircled by a red dwarf companion. Except this time the two are separated by such an enormous distance that it takes them upwards of 100,000 years to complete an orbit. Nevertheless, the target was 777a and it's home to 3 confirmed planets. 2 of them are many times more massive than Earth and are practically hugging the star, while the third is a bit more massive than Jupiter and is much further away. In between them lies the habitable zone, which does appear to be stable enough to host an Earth-like planet, but none have been detected to date. While all of these stars are within the general solar neighborhood, we still have to wait until the 22nd century until any response could relativistically be received. A fact that might come as a disappointment to some of you, but no doubt a relief to others.
You see, it's not that I'm paranoid. I feel that there will be many civilizations that want to be our friends. However, it only takes one with a contrary point of view to ruin our day, our existence. Before people start sending signals into space on my behalf, I'd like them to ask for my permission.
But it wasn't just the general public. A growing number of experts had begun to question the ethics and wisdom of deliberate communication attempts. Among them was Carl Sagan, who as early as 1983 began arguing in favor of listening rather than sending. Not so much because he feared invasion, but because he felt that contacting aliens was premature. He wrote that it is not yet clear that we have anything particularly interesting to say due to what he described as our backward status. In other words, a baby civilization like humanity probably won't have much to offer one that's been around for millions or billions of years, so we should prioritize intelligence gathering before we start shouting at the sky. But astronomers like Alexander Zaitsev strongly disagreed with that position, essentially arguing that we must not give in to fear of the unknown. Sure enough, just a few months after the first cosmic call, Zaitsev and others began work on yet another message. In early 2000, a youth community center in Moscow was preparing to host a festival to celebrate the new millennium. During the preparations, an astronomy teacher named Boris Chanichner suggested to some of his students that they should create an interstellar message to be presented during a space-themed portion of the event. The project was spearheaded by 2 teenagers named Igor Kiselev and Vladimir Filipov, who quickly devised a message composed of both music and pictures. Once the project had been approved by a committee that included Alexander Zaitsev, it was decided to transmit the message sometime the following year to commemorate the 40th anniversary of the first crewed spaceflight by cosmonaut Yuri Gagarin in 1961. Zaitsev expanded upon the ideas of Kiselev and Filipov by suggesting the message be divided into 3 distinct signal types: constant, continuous, and discrete. The constant signal would be sent first to let the aliens know they've picked up something strange. That probing beacon would then transition into a continuous signal conveying the musical component of the message. Finally, 2 discrete frequencies would be used to broadcast binary-coded images. According to Zaitsev, the 3 formats represented a language of nature, emotion, and logic. A total of 9 musical compositions were selected, and Zaitsev proposed using an electronic instrument known as a theremin, partly because it generates a smooth monophonic signal with minimal overtones, but also because the theremin was a Russian invention. The visual portion of the message was composed of 28 bitmaps primarily designed by Kiselev and Filipov. The first image depicts a wave within a circle, which is meant to convey to the aliens that the circle's diameter is equal to the wavelength of the transmission. If they correctly make that guess, the next image is meant to be scaled so that this circle with a human face in the center matches the diameter of the circle from the previous image. Doing so would enable them to decode other components like how this wavelength corresponds to a spectral absorption line of water. Without going into too much detail here, it's meant to highlight the significance of water to life here on Earth. While some of the illustrations try to convey information using science and logic, a lot of it was artistically motivated. Life inhabits the ocean, land, and atmosphere, represented by dolphins, humans, and birds that the aliens will of course have no chance of deciphering. The 10 circles along the edge, numbered 1 through 10, not only symbolize our use of a base 10 numeral system, but also correspond to the next 10 images. The first of which is this side view of our galaxy with an arrow pointing at us. The second is a schematic of the solar system. The third gets a bit closer. The fourth gets closer still. Then there's a family, a house, and a close-up of a person. Towards the end, there's also a yin and yang symbol, 2 games of tic-tac-toe, and an illustration of the telescope used to transmit the message. But it doesn't end there, because the next image is the same emblem we saw before, except the 10 outlying circles have now been filled in with the 10 preceding images. Exactly why they're laid out in this circular pattern in this particular order, or even what function it all serves, I couldn't tell you. But again, the emblem was intended to be both informational and artistic. Following the emblem sequence, the next 3 images contain some text written in both Russian and English. Approximately 1,000 students between the ages of 13 and 18 participated in the project, and this is an extreme abbreviation of their many proposed greetings. It very innocently ends with,
"We wish you peace and love,"
signed by
the children from the earth.
The final 12-bit maps depict illustrations that we've already seen, each one captioned with a brief description in both Russian and English. They're meant to function as a sort of dictionary with the hopelessly optimistic goal of teaching the aliens how to read the aforementioned greeting. The 3 components of the message, starting with the probing signal, followed by the music and the 28-bit maps, were then transmitted from the Yevpatoria Deep Space Center on August 29th, 2001. Much like the first cosmic call, the teenage message was transmitted multiple times over multiple days, this time to 6 different targets. The first one was Gliese 797A, an as of yet planetless but sun-like star that forms a wide ternary system with 2 smaller companions. The second target was 37 Geminorum, a solitary sun-like star that has yet to show any signs of hosting a planetary system. Target number 3 was another sun-like star known as 47 Ursae Majoris, which is home to 3 confirmed planets. They all appear to be gas giants, and the one closest to the star is grazing the outer edge of the habitable zone. Because it's more than twice the mass of Jupiter, its immense gravity renders nearly the whole outer half of the habitable zone completely off limits. An Earth-like planet within this region simply wouldn't be able to maintain a stable orbit. But if such a planet were to be located further inwards, things look a lot more optimistic. The fourth target was Gliese 547a. Once again, it's a Sun-like star that forms a wide binary system with a small brown dwarf companion. Apart from that, no planets as of yet. Target number 5 was yet another Sun-like star known as Gliese 327 with no confirmed planets. It does, however, show signs of being surrounded by either one or multiple belts of debris, but the precise mass, composition, and extent of this debris remains to be seen. Finally, the sixth target was Gliese 788. It is yet another solar analog with neither stellar nor planetary companions. All but one of the targets are more than 50 light-years away, so the minimum response time is over a century. The one exception is 47 Ursae Majoris at 45 light-years, so we could hear back from the Majorans as early as 2092. As the name Encounter 2001 would seem to imply, the Millennial Voyage was scheduled to launch by the end of 2001, but shortly before the start of that year, the project was quietly rebranded as Team Encounter. While it's difficult to know exactly what was going on behind the scenes, it seems like they vastly overestimated the public's interest in sending messages into space.
In this pre-lecture, we will focus on statics, the study of forces on objects that do not move. We will start by looking at the torque produced by the weight of a solid object, and will find that it can be calculated by simply assuming that the entire mass of the object is located at its center of mass. We will then move on to determine the general conditions that must be satisfied for a system to be in static equilibrium. First, the sum of all the forces acting on the system must be zero. Second, the sum of the torques produced by the forces acting on the system must also be equal to zero. We will close by applying these conditions to a few specific examples. Up to this point, we have considered the torque due to forces whose point of application was clear. The tension in a string wrapped around a cylinder provides a force acting at the edge of the cylinder, as does the force of friction acting on a ball rolling down a ramp. We now want to consider torques due to continuous mass distributions. We will show that the torque produced by the weight of a solid object can be calculated by simply assuming that the entire mass of the object is located at its center of mass. Here we see a thin beam attached at one end to a wall by a hinge. The hinge can rotate freely, so when the beam is released, it will start to swing downward as shown. Clearly, the gravitational force is producing the torque about the rotation axis defined by the hinge. To calculate this torque, we need to integrate the contributions due to all of the mass elements dm along the length of the beam around this axis. Each mass element will produce a torque into the screen so that all we need to do is to set up an integral to determine the magnitude of the torque. After taking provides a force acting at the edge of the cylinder. The application was clear. The tension in a string wrapped around a cylinder provides a force acting at the edge of the cylinder, as does the force of friction acting on a ball rolling down a ramp. We now want to consider torques due to continuous mass distributions. We will show that the torque produced by the weight of a solid object can be calculated by simply assuming that the entire mass of the object is located at its center of mass. Here we see a thin beam attached at one end to a wall by a hinge. The hinge can rotate freely, so when the beam is released, it will start to swing downward as shown. Clearly, the gravitational force is producing the torque about the rotation axis defined by the hinge. To calculate this torque, we need to integrate the contributions due to all of the mass elements dm along the length of the beam around this axis. Each mass element will produce a torque into the screen so that all we need to do is to set up an integral to determine the magnitude of the torque. After taking the constant terms outside the integral, we are left with the integral of r dm. Now, this integral is exactly the integral that is needed to calculate this torque. We need to integrate the contributions due to all of the mass elements dm along the length of the beam around this axis. Each mass element will produce a torque into the screen so that all we need to do is to set up an integral to determine the magnitude of the torque. After taking the constant terms outside the integral, we are left with the integral of r dm. Now, this integral is exactly the integral that is needed to determine the position of the center of mass. Therefore, we can replace the integral in our expression for the magnitude of the torque by the distance from the hinge to the center of mass. The resulting expression for the magnitude of the torque is, as promised, just equal to what we would obtain for a point particle. The contributions due to all of the mass elements dm along the length of the beam around this axis. Each mass element will produce a torque into the screen so that all we need to do is to set up an integral to determine the magnitude of the torque. After taking the constant terms outside the integral, we are left with the integral of r dm. Now, this integral is exactly the integral that is needed to determine the position of the center of mass. Therefore, we can replace the integral in our expression for the magnitude of the torque by the distance from the hinge to the center of mass. The resulting expression for the magnitude of the torque is, as promised, just equal to what we would obtain for a point particle located at the center of mass of the beam, and whose mass is equal to the mass of the beam. This result is completely general and is true for any shape. We chose a thin beam for this example just to simplify the calculation. In the last slide, we found that the torque on a solid object about some rotation axis due to gravity can be found by assuming that the weight of the object acts at the center of mass of the object. We will now examine this result in more detail to obtain an alternate expression for the torque. From the definition of the cross product, we know that the magnitude of the torque can be found by multiplying the magnitude of the vector from the rotation axis to the center of mass of the object times the magnitude of the weight times the sine of the angle between them. Since the weight always points down, the product of RCM and the sine of this angle will always be equal to the horizontal displacement of the center of mass from the rotation axis. In other words, the magnitude of the torque on some object due to gravity about any rotation axis is just the weight of the object times the horizontal distance that the center of mass is displaced from a vertical line through the axis. This result makes sense. For example, the torque due to gravity will be zero if the center of mass is directly below the axis. The object will just hang there without moving. This result also implies that the torque is biggest when the object is rotated so that the center of mass is at the same vertical height as the axis, making the sine of the angle between RCM and the weight its maximum value of 1. It's important to note that the torque will always have the form we see here. It can't always be expressed as a product of a force and the perpendicular distance of a line through this force and the rotation axis. This perpendicular distance is called the lever arm. In the case of gravity, we see that the lever arm is just the horizontal displacement of the center of mass from the rotation axis. In general, the lever arm does not have to be horizontal, but it will always be perpendicular to the force. On the next slide, we will do an example that illustrates this calculation. Here we see a horizontal beam having a mass m and length L attached to a vertical wall by a hinge. The far end of the beam is supported by a massless wire that makes an angle theta with the beam. Our job is to determine the tension in this wire. We begin by drawing and labeling all forces acting on the beam. The weight acts at the center of mass, and the tension due to the wire acts at the end of the beam in the direction of the wire. There is also a third force, due to the hinge, which supports the beam at the wall. We will allow this force to have both x and y components. Since the system is static, both the acceleration of the center of mass and the angular acceleration about any rotation axis must be zero. Since the acceleration of the center of mass of the beam is zero, the total force on the beam must be zero in both the x and y directions. Therefore, we can write down two equations that must be true. These two equations alone do not allow us to solve for the tension in the string, since there are three unknowns: the tension and both components of the force due to the hinge. The good news is that we can get another equation by realizing that the angular acceleration of the beam about any axis is zero, which means that the torque about any axis must also be zero. We now want to choose an axis of rotation for the calculation of the torque that simplifies our calculation. Since our task is just to find the tension in the wire, we can pick a rotation axis perpendicular to the screen that passes through the hinge. We see immediately that the lever arm of the force due to the hinge is zero about this axis, so the torque due to this force about this axis is also zero. What about the torques due to the other forces? The magnitude of the torque due to the weight of the beam is just equal to the weight times its lever arm. Using the right-hand rule, we see that the direction of this torque is into the screen. The magnitude of the torque due to the wire is equal to the tension in the wire to determine the tension in this wire. We begin by drawing and labeling all forces acting on the beam. The weight acts at the center of mass, and the tension due to the wire acts at the end of the beam in the direction of the wire. There is also a third force, due to the hinge, which supports the beam at the wall. We will allow this force to have both x and y components. Since the system is static, both the acceleration of the center of mass and the angular acceleration about any rotation axis must be zero. Since the acceleration of the center of mass of the beam is zero, the total force on the beam must be zero in both the x and y directions. Therefore, we can write down two equations that must be true. These two equations alone do not allow us to solve for the tension in the string, since there are three unknowns: the tension and both components of the force due to the hinge. The good news is that we can get another equation by realizing that the angular acceleration of the beam about any axis is zero, which means that the torque about any axis must also be zero. We now want to choose an axis of rotation for the calculation of the torque that simplifies our calculation. Since our task is just to find the tension in the wire, we can pick a rotation axis perpendicular to the screen that passes through the hinge. We see immediately that the lever arm of the force due to the hinge is zero about this axis, so the torque due to this force about this axis is also zero. What about the torques due to the other forces? The magnitude of the torque due to the weight of the beam is just equal to the weight times its lever arm. Using the right-hand rule, we see that the direction of this torque is into the screen. The magnitude of the torque due to the wire is equal to the tension in the wire times its lever arm. Using the right-hand rule, we see that the direction of this torque is out of the screen. Therefore, the two torques are in opposite directions, so that we assign them opposite signs. We can solve the resulting equation to find a simple relationship between the tension in the wire, the weight of the beam, and the angle of the wire. We can now determine the force the hinge exerts on the beam by solving our two original equations we found using Newton's second law after substituting in our newly found value for the tension in the wire. We will now change the geometry of our beam and wire example and determine the force at the hinge as well as the tension in the wire. Now once again we start by writing down Newton's second law for both the x and y components. We can immediately solve the y equation for f sub y. The x equation, though, contains two unknowns, the tension and the x component of the force exerted by the hinge. To solve for these two unknowns, we need to write down the torque equation. We again pick a rotation axis through the hinge, making the torque due to the force of the hinge 0. The magnitude of the torque due to the weight of the beam is equal to the weight times its lever arm. Using the right-hand rule, we see that the direction of this torque is into the screen. The magnitude of the torque Using the right-hand rule, we see that the direction of this torque is into the screen. The magnitude of the torque due to the wire is equal to the tension times its lever arm. Using the right-hand rule, we see that the direction of this torque is out of the screen. The two torques are once again in opposite directions so that we assign them opposite signs. We can solve the resulting equation to find a simple relationship between the tension in the wire, the weight of the beam, and the angle of the wire. If we now return to the Newton's second law equations, we see that the magnitude of its x component is equal to the tension, and the magnitude of its y component is equal to the weight of the beam. The procedure we have demonstrated in these last two examples will work well for any statics problem. Namely, start by drawing a picture that shows all forces and where they act. Using this picture, you can write down equations that determine that the translational and angular accelerations are 0. You are free to choose a rotation axis that is out of the screen. The two torques are once again in opposite directions so that we assign them opposite signs. We can solve the resulting equation to find a simple relationship between the tension in the wire, the weight of the beam, and the angle of the wire. If we now return to the Newton's second law equations, we see that the magnitude of its x component is equal to the tension, and the magnitude of its y component is equal to the weight of the beam. The procedure we have demonstrated in these last two examples will work well for any statics problem. Namely, start by drawing a picture that shows all forces and where they act. Using this picture, you can write down equations that determine that the translational and angular accelerations are 0. You are free to choose a rotation axis that simplifies the calculation of the torques. We will close this pre-lecture by considering what happens when the wire in the previous example breaks. What is the angular acceleration of the beam as it falls? Here we see the string break and the beam rotates about the hinge. This motion is a pure rotation, whose angular acceleration can be determined using the torque equation. Since the wire is no longer attached to the beam, the only torque around this rotation axis is that due to gravity. On the last slide, we determined both the magnitude and the direction of this torque. We can therefore determine the magnitude of the angular acceleration by simply dividing this torque by the moment of inertia of the beam around the rotation axis. Previously, we determined that the moment of inertia of a beam about its end is equal to 1/3 its mass times the square of its length. The first thing to note about our result is that the angular acceleration is not constant. It depends on the angle theta. It is biggest when the beam is horizontal and smallest when it is vertical. Of course, the angular displacement and the angular acceleration are not independent variables. If we write alpha in terms of the second derivative of theta with respect to time, we obtain a differential equation. This equation is difficult to solve analytically, but we can, and we will, solve it in the small angle approximation in a few pre-lectures when we discuss simple harmonic motion. We conclude with a brief discussion of the main points of this pre-lecture. First, we determined that the torque produced by the weight of a solid object can be calculated by simply assuming that the entire mass of the object is located at its center of mass. Second, we found an alternate expression for the magnitude of any torque as simply the product of the force and its lever arm, the perpendicular distance of a line through this force and the rotation axis. Third, we investigated the conditions for static equilibrium and applied them to a few specific examples. In particular, we observed that for a system to be in static equilibrium, the acceleration of the center of mass and the angular acceleration about any rotation axis must be zero. Consequently, the requirements for a system to be in static equilibrium are: 1. The sum of all the forces acting on the system must be zero, and 2. The sum of all the torques produced by these forces must also be zero.